Okay, welcome to equilibrium. The equilibrium is basically defined as the net force equal to zero. In some cases, that's the object not moving. Other cases, the object is moving with a constant velocity. In these problems, we'll be looking at the objects being stationary. So, typical problem is the seesaw or the teeter-totter, depending on where you're from. Um, you have an object that's balanced, and the point at which it's balanced, right here, is called, let's see, it's called the fulcrum. Let's see if I can write this. Fulcrum. Okay, that is the balancing point on a seesaw. Okay, it is really our axis of rotation. Because if it's allowed to spin, it will spin on that point. And so this is our axis of rotation. Now, seesaws are often used on playgrounds. So, for example, if I fast forward here, you are sitting on a seesaw. If you sit down on this seesaw, what will happen? So, if you sit, it will spin. I don't think that's really hard to imagine. So if there's nobody on the other end, this thing will spin, and it's actually going to spin clockwise, which I will abbreviate CW. So anytime you have a clockwise motion, it is abbreviated CW. And if I think you're all familiar with clockwise, it's basically the way the hand on a clock will turn. So if you sit on this side, you'll start this thing spinning in a clockwise direction until something interferes with the motion. Okay, now um, the force, in other words, or maybe more specifically the torque, acting on this object is equal to, as you know, RF sine theta. Now let's assume you have good posture and you're sitting at a right angle, and so this becomes 1 because you're sitting up straight. Sit up straight, as your parents might tell you to do. And so the torque here, assuming that you're sitting up straight, is equal to the distance from the fulcrum and your weight. Whether you call it Fg or W doesn't matter. It's your weight times the distance away from the fulcrum. That is the torque that you apply to this teeter-totter. Okay, now, you don't want it to just spin, and actually if you're the only one sitting on the teeter-totter, you will probably not get much out of it. You need somebody to join you. And so you get your little brother or little sister to join you. So what we know is that you have a force and you have a weight, and that provides a torque. And it is a clockwise torque because you would make it spin in a clockwise direction. Well, your little brother has a different distance and a different weight, and I'll just say sibling. Maybe I'll abbreviate it S, or whatever the case is. And this is counterclockwise. Oop, I gotta get a K in there, sorry. Counterclockwise, and I will abbreviate that CCW. So you have a clockwise torque coming this way, counterclockwise torque coming this way. And in order to achieve balance, for balance, the counterclockwise torque has to equal the clockwise torque. That's important. Which means, if I can scroll down a little bit, which means that FR for your little brother is equal to FR for you. Okay? Balanced torques. Now, if you weigh more than your brother, you need to sit closer. Your brother has less force, so they need to sit farther away. That's the basic. So the lighter something is, the farther away from the fulcrum, farther away from the axis of rotation they need to sit in order to balance out the heavier weight. That is the basics of equilibrium. Now, let's see if I can get to the next one here. The suspended object. Now this is one that doesn't necessarily involve torque, but it's the type of problem that you're likely to see. This is an equilibrium with free body diagrams. I'm just going to do FBD equilibrium. In this problem, all the forces have to balance. So the net force is equal to 0. Now we have three forces here. We have, let's just call it tension 1. We have tension 2, and we have the weight. These three forces must be balanced. Now, what I think you'll notice, and I put numbers in here, but I'll try and do this without numbers. What I think you'll see is that this component of tension 2 has to balance T1. So T1 equals, and I'm going to just go right there and say T2 cosine theta. This upward part, this part here, which can be completed as the outer side of the triangle, this part of the force has to balance the weight of the object. So it's safe to say that the weight of the object has to equal T2 times the sine of the angle. Now, at this point, you have to have certain numbers. I can give you the mass, I can give you the angle, and if you have the mass, you can get the weight because that's just mg. And so, for example, 10 times 9.8 gives you 98 newtons of force. And so over here, we got 98 is equal to T2 times the sine of 30 degrees, which of course is just 0.5. So T2 ends up being 196 newtons. Well, then you come over here, and by over here, I mean T1. I know that T2 is 196 newtons because of this. And I know cosine of 30 degrees, well, what is it, square root of 3 over 2? Your calculator should be able to tell you something about this. So 196 times the cosine of 30, let's see, 196 times 0.866. Let me get the calculator up here. 196 times 0.866 should give me 169 point, let's see, T1 is, oh, I just lost it, didn't I? 169.74, 169.74 newtons. Now, just a quick review. We have one mass, one angle, three forces. Use the weight to help you get T2. Once you know T2, you come back to find T1. That is a basic equilibrium problem involving two ropes and a hanging mass. And I think that should do it for now. We'll do another video where there's the window washer, but I think we've got enough for this one.